So, welcome to this. This is the Further Maths Support Programme online revision session for AQA S1, and in this session we're going to be looking at the ideas of estimation. So it's quite a big topic. So firstly we need to understand the words population and parameter. They link together, sample and statistic. Because you need to make sure you know what you're dealing with to be able to find the correct unbiased estimators. So again, based on that, we need to find unbiased estimators of population mean and population variance. We need to understand what the concept of a sampling distribution is of the sample mean. Based on that, understand when it is appropriate to use something called the central limit theorem. You don't need to be able to prove it, which is good. You don't need to be able to do that at all, but you do need to be able to justify its use. Based on that, you need to be able to understand and use confidence intervals and make some inferences, so some sort of fundamental ideas leading on to hypothesis testing without formally doing it. So you're given quite a lot of information on a formula sheet, which is great. So we're told that capital X bar is an unbiased estimator for the population mean. Okay, so mu is a parameter, a population parameter. X bar is a sample statistic. So there's nice alliteration of words going on there. And we're also told that S squared is an unbiased estimator. Now, we don't need to worry too much at this level what that means, but you need to appreciate that it's going to be the best guess that you can with the data given for the parameters given. Okay, so as we discussed earlier, this n-1 is very, very important. Now there is another way of writing this which is slightly easier to deal with, which is 1 over n-1 times by the sum of x squared minus the sum of x all squared over n. Okay, so there's alternative forms for this equation as well, just to make you aware that sometimes it's easier to use other things. Also, we're told about the sampling distribution of the mean, okay, of the sample mean. And it's very, very similar to standardizing, other than we've got sigma over root n when we standardize here, because we're using something called standard error. So, January 2011, question 3. It's a big question. So the volume x litres of orange juice in 1 litre carton may be modelled normally with an unknown mean of mu. The volume x litres recorded to the nearest 0.1 litre is given below. So I've got quite a lot of data and it's grouped and everything. So let's look at what the question's asking. It says for the group 0.98 to 1, show that it has a midpoint of 0.99 litres. Okay, so we do need to do this. We do need to show. And the way we do that is by demonstrating how we find a midpoint. So a midpoint is by adding the two ends of the interval together. It's a mark that's very easy not to get because, well, showing this is quite interesting. It then says, state the minimum and maximum values that could be included in the group. Well, what we're doing there is we're actually looking at the boundaries of the group. So 0.98 could be anything from 0.975 upwards. Likewise, if it's going to 1, it could be as high as 1.005. So those would be the bounds for that number. And again, what you're going to get is a B mark for doing that. We're then asked to calculate the mean and standard deviation of these 100. So we've got to understand that we're dealing with a sample here. This is going to be very, very, very important about how we do this. So as we've seen in other videos, x bar is going to be the sum of fx over n, and s squared, we'll square root it to find the standard deviation, is 1 over n-1. Like we've just said, it's best to use this definition, sum of fx squared minus the sum of fx squared all over n. Okay, so to do this we need three values. We need n, we need sum of fx, and we need the sum of fx squared. And they've given you a hint by asking you to use midpoints. Okay, so they've given you a heads up about how this works. We multiply and add. So what values have we got that are important? Well, we've got sum of fx, and the sum of fx turns out to be 106.2. And we've got the sum of fx squared, which turns out to be 112.9662. And n is 100. So we've now got everything we need. Okay, so x bar comes out as being 106.2 divided by 100, which is 1.062. And s squared, and don't forget we'll need to square root this at some point, is going to be 1 over 99 my pen starts to work. So 1 over 99 1 over 99 times by sum of fx squared, 112.9662, minus the sum of x, 106.2 squared, over 100. And then we're going to square root that. And that will lead me to a value of s of 0.0043. So 3 marks, you're going to get a selection of B marks here. So you're going to get a B mark for working out the mean, and then you're going to get 2 B marks for working this out. So your first B mark is for making sure that you have got the correct form and the correct values, and the second B mark clearly for then getting the correct answer. Okay, so now we've got to construct this thing called a 99% confidence interval. So the definition of a confidence interval is that it's x bar plus and minus some z value at some significance level times by sigma over root n. That's the definition. What we need to work out and state is what this value of z is. Okay, so x bar we've worked out. We just worked that out from the calculation, so 1.062 plus and minus. So the value that we're dealing with here is a 99% confidence interval, so it's two-tailed. So to do that, we look it up in our tables to find that z is 2.57. So we're going to have 2.57 times by sigma, which we've just worked out, 0.043, divided by root n, which is root 100. Okay, and what that's going to do for you is trigger your B mark for this question. Okay, it also triggers the method mark because you've shown some understanding about how we're going to set up the formulae. So we just then need to calculate this. So your confidence interval is going to be 1.06 plus or minus, if you work that out, it's only 0.01, it's quite tiny. So we could do with then writing it fully like this. So you then get an accuracy mark for working this through. Okay, and then a final accuracy mark for writing the correct interval. So for part 2, give a reason why the confidence interval is approximate rather than exact. Well, we've got to really make sure we understand what's going on here. Okay, so one sort of thing is your pet. Oh, I've missed part B. Hang on. Oh no, okay. So it's because your sample data is grouped. Okay, because it's grouped, you don't actually know your full data, if that makes sense. Oh, let's go back. Okay, so because it's grouped, you don't actually know your data. Bear with me a second, I'm having some issues with my pen. So here we can state that sample data is grouped. So we don't know our actual data. That's quite an important thing. We could say that, well, anything really indicating that it's grouped will do. You don't know your actual data. So that will get you a B mark. We're then asked to support the claim that mu is greater than 1. Okay, so if we go back to our confidence interval, we could see that our 99% confidence interval was 1.05 to 1.07. And because the confidence interval is wholly above 1, then this infers that mu therefore is greater than 1. Okay, it's only an infer at this particular point. Okay, and then for the final aspect, we've got to work out the probability that x is between 0.94 and 1.16, being roughly equal to 1. Okay, so if we think about this, we can clearly see that we've got some symmetry about 1. Okay, so what we argue is that nearly 99 to 100% of data is between these values. We can see that from the data. Okay, and because that's true, then we can say that the probability is roughly equal to 1. Okay, so again, it's just testing your understanding really about what's going on in that situation. Okay, so slightly different question. An ambulance control centre responds to emergency calls in a rural area. The response time T is defined as the time between answering the emergency call at the centre and arrival. Response times have an unknown mean and an unknown variance. Okay, so Anita, the centre's manager, asks Peng, a student who's on work experience, to record and summarise the values of T obtained from the 80 emergency calls. And she does this, and she works out that T bar is 6.31, and she works out that S squared, so the unbiased estimate of the variance, is 19.3. Also, we're told that only one of the 80 values of T exceeded 120. So we could rewrite this if you wanted as the probability of T being greater than 20 is equal to 1 out of 80, if you wanted to write it in that way. So, let's see what the question is asking. Anita then asks Peng to determine a confidence interval. Peng replies that from his summary results, T was not normally distributed, and so a valid confidence interval could not be constructed. So, we've got to explain why, using this particular value, Peng's conclusion is likely to be correct. So let's calculate this, T bar minus 2s. So that's going to give me 6.31 minus 2 lots of the square root of 19.3. Okay, and if we work that out, that's going to give me negative 2.48. Well, you can't have negative time. Okay, and that's what we're claiming here, because this is a statistic that's about a confidence interval. So we can't have negative time, so that's why it can't really be normally distributed, because this value doesn't really exist. Explain why Peg's conclusion that a valid confidence interval could not be constructed was incorrect. Well, here n is large, and as long as n is large, we can always create a confidence interval. So we've got some indication that that's going to be the case. What can we use? So if n is large, we use the central limit theorem. We use the central limit theorem to create the confidence interval. Okay, so when we talk about large, we're talking about greater than 25. So for this second part, you get a B1 for y, and then another B1 for stating the rationale behind that. Okay, for the first part, you get B1 for doing the calculation, and then B1 for making some form of statement based on that. So what we are asked now to do, however, is to construct a 98% confidence interval. So again, if you look up your 98% confidence interval, that's going to lead you to a two-tailed z value of 2.32. Okay, and you'd look that up in your normal table. So as before, our confidence interval is going to be T bar plus or minus 2.32 times by S over root n. And now it's just a question of calculating that. You're going to get 2 marks now, an M1 and a B1, same as it was in the previous question. So now we've got 6.31 plus and minus 2.32 lots of the square root of 19.3 divided by the square root of 80. Okay, and that's going to give you an A mark, and we'll give you follow through. So again, if you got the wrong B value, you would this value here for Z, you would still get marks. Okay, so if we calculate these, that's going to give me a confidence interval of somewhere between 5.16, sorry, and 7.46. There is some tolerance on this, so it could be 5.18, all the way up to 7.44. So anything in those sort of ranges will get you the accuracy mark for this. So in part C, Anita has two targets for t, and these were that mu must be less than 8 and that the probability of having fewer than or equal to 20 exceeds 95%. And what we've got to do with justification is whether each of these targets is likely to be met. So let's consider mu t being less than 8. Now, that's as before, we can conclude that this is true because your confidence interval 5.16 to 7.46 we can say is wholly wholly below 8. So therefore indicates or infers that actually the population mean is probably less than 8. Now let's look at the other one. So let's turn it round. So what we have here, if it's going to let me do this, what we have is the probability of t being less than 20 being greater than 95%. So if we turn that round, that's going to be the probability of t being greater than or equal to 20 equaling 0.05. Now, we've already made a statement in this that we know that the probability of t being greater than 20 is in fact 1/80th. Okay, which is 0.013. Okay, so is this true? Well, yes, again it's true because we know that 0.013 is less than the 0.05. So again we can imply that this is true. So this is less than, sorry, if it's greater than 0.5, this has got to be less than 0.5. So it's less than 0.05. So again we can state yes, second target is going to be correct as well.